Assalamualaikum. My name is Marsha Naima binti Ismail Naim with a metric number of CD21027. I will be presenting about the theory of crank motion. An adaptable coupling or widespread joint is habitually utilized to interface with two shafts and transmit circular movement from the other. Indeed, persistent circular movement is maybe the single biggest thing that mankind produce in the world with the accessibility, vitality. An all-inclusive joint is basically a combination of machine components which transmit turn from one pivot to another. Shafts are utilized to transmit rotating movement, and in most cases these shafts turn in orientation set in a straight line. Be that as it may, there are cases where the shaft cannot be straight and it has to be worked through an point X. A great illustration in common utilized is the shaft, which transmits 60-stick control from an engine car motor through its gearbox to the back pivot to drive the race wheels. Here, the shaft is for the most part at an point, and the operation is encouraged complicated by the truth that the point shifts when the engine car runs over bumps in the streets. An issue like this can be fathomed by the utilization of all-inclusive couplings, known as widespread joints. The widespread coupling device is a straight bar with couplings based on the basic and cardinal rules. The couplings are not steady-state couplings. Such condition can be fulfilled by the utilization of widespread couplings as appeared at the A and C. For uniform control transmission, the plan and get together of the two couplings must be carefully considered.
Good day, sir. My name is Junlin Jaji, matrix number DD220050. So I'll be presenting the procedure part for this experiment. Step 1. The panel board is set up as shown in the figure below. These are the apparatus we have in our lab. Step 2. A weight of 10 Newton is placed on the weight hook, making a total weight 10.1 Newton. The crank is pulled into flat position, generally called the dead center, which is at the angle of 0 degree. Next, the 10 Newton spring balance with an adjustable hook is hung. The spring balance value is ensured to be 0 before the experiment begins. Step 4. The adjustable hook is shifted until the angle is 10 degree. We can increase the angle to 10 degree by turning the circular plate as circled in the figure below. At 10 degree, make sure the piston is fixed and the spring balance reading is recorded from the spring balance scale. Lastly, step 4 is repeated, each time increasing the angle by 10 degree. The final angle is 180 degree from 0.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fahad Bingan Muludin, our matrix DD220052. So today, I will like to continue the presentation with result and calculation. Based on the experiment of crank motion, the centrifugal force is received during the experiment based on the crank angle, which is 0 degree until 180 degree. For experimental turning moment, we calculate the centrifugal force times by 47.5. Okay, this is the graph that we have obtained from the experiment of crank motion. The highest turning moment for theoretical is 206.4 Nm, and the highest turning moment for experimental is 142.5 Nm.
The observation of the crank motion is as soon as the 10 Newton being placed on the weight hook, there is a positive error occur which is on the spring balance. The spring balance in this experiment is not functioning well as it cannot ensure the value of the spring balance becomes 0 reading. In order to find the value of the centrifugal force, the value must be subtracted with the positive order value to obtain the correct value of the particular crank angle. When the crank angle increases from 0 to 90, the value of centrifugal force is also increasing, but it starts to decrease when the crank angle increases from 90 up until 180. From the table shown, the experiment value for the turning moment tends to not agree with the theoretical part of this experiment. This might happen due to the inefficiency of the apparatus itself.
Now, I will continue with the sample calculation of current motion. For the experimental turning moment value, we need to calculate using the centrifugal force times by 47.5. For the first angle, which is 10 degree, we need to calculate 0.5 times 47.5 and we will receive 23.75 for turning moment. And the step is repeated until 180 degree. For percentage of difference, we need to calculate using theoretical value minus experimental value divided by theoretical value times 100. For the percentage of error, for the first angle is 56.97%. That is all from me. Thank you.
So I will continue the presentation with the discussion. So the first discussion is discuss the graph obtained. So the graph follows a quadratic pattern and the maximum value for theoretical is 260.4, but we get the experimental value is 142.5 Newton meter for the turning moment. So according to the graph, the experimental turning moment peaks at 90 degree, whereas the theoretical turning moment reaches the maximum at 80 degree. So for the second discussion, compare results between theoretical turning moment and experimental results. So for theoretical turning moment, the first one is the maximum value, which is 260.4 Newton meter. And for the experimental turning moment, the maximum value is 142.5 Newton meter. And for the second one, the crank angle revolution is at 90 degree when the maximum happened. And for experimental turning moment, the crank angle revolutions is at 80 degree when the maximum happened.
Hello everyone, my name is Martin. I would like to continue the discussion part. Firstly, I would like to discuss at what angle did the turning moment reach maximum. From the experiment, it shows that the turning moment reached a maximum of 142.5 Newton millimeter at angle of 90 degree, while the theoretical maximum was predicted at 80 degree. For turning moment, it can be calculated as the product of radius and centrifugal force. Due to the constant radius, turning moment will increase with centrifugal force. Therefore, when the connecting rod is most perpendicular to the crank center line at 90 degree, it means that centrifugal force had reached its maximum, so turning moment also reached its maximum at the same time. Next, I would like to discuss how many maximum turning moment values are reached during each revolution of the crank. During each revolution, the turning moment reaches two maximum values. As the crank rotates, it will rotate from the top tip center to the bottom tip center, and then back to the top tip center for one revolution. So, the turning moment will reach maximum twice, at 90 degree and 270 degree respectively, as shown in the graph attached. Last but not least, I would like to discuss two examples of crank mechanism application and explain how it works. The first example is the internal combustion engine. As a fuel air mixture inacts, it pushes the piston down and the connecting rod in it will translate the linear motion to the crank arm. The crank arm then converts to the push into rotational force on the crankshaft until the turning moment reaches its maximum at 90 degree, which can be used to drive the other engine components. The second example is the bicycle pedal. It will convert the rider's leg strokes into rotational motion of the rear valve. By pushing down the pedals, crank arms are rotated around the bottom bracket and turning the chain ring, which will drive the chain so that the chain can rotate the rear valves for moving the bicycle. That's all from me. Thank you.
Hi, it's me again, and I'll be presenting the conclusion. The key observation of this experiment are: first, torque and angular velocity vary inversely in a sinusoidal pattern. Secondly, the theoretical maximum turning moment is 260.4 Newton millimeter at 80 degree. Thirdly, the experimental maximum turning moment is 142.5 Newton millimeter at 90 degree. The errors we have in our experiment is between 54% to 57% due to factors like friction. Next, I would like to talk about the importance of knowing how the turning moment acts while the degree of a crank varies. It is important to know it as it helps us to optimize, for example, engines and bicycle pedals or anything that use a crank mechanism. Apart from that, it also helps us to ensure the durability and the reliability of the crank mechanism. For the future work and improvement, we can improve the experimental setup. For example, making the movement of increasing the angle of the crank much more easier and stable. That's all from our group. Thank you for lending us your ears.